Now we have the last talk of the morning session. Miquel Cueca from Göttingen University is going to speak about sigma models.
Okay. Thank you very much for the invitation. It's always a pleasure to be here in Rio de Janeiro, even more if it's winter in Germany, you know. So this is a joint work with Alejandro Cabrera, and it's just an ongoing project that we are trying to understand a bit what are the current sigma model. So in this talk, what I want to try to do for you is look into Poisson manifolds, but with the glasses of quantum field theory. So let me try to explain what I understand, or in this talk, what we use as a quantum field theory. So we just need a space of fields that normally is infinite dimension, like maps between two manifolds or sections of a vector bundle or flat connections or whatever. And then we need an action that is just a function over this space of fields. And then we came up with this path integral. And this is like the main thing of this talk. So this formula of the path integral is just not mathematically well defined, so it's just an heuristical formula that we have over there, because the space of fields is infinite dimension, then make sense of what is the measure over that space is difficult, and normally the action has some symmetries, and if you want like something invariant, some measure invariant under these symmetries is just normally impossible. So what we want to make sense is of this heuristical expression of the path integral. And I will put it here because it's like what will motivate just all the rest of the talk. So, okay, what we need to care about these kind of examples. So, well, one example is, for example, the derivation of Cattaneo-Felder of the Kontsevich star product using the Poisson sigma model. And the way that more or less he did is to make sense of this path integral using some kind of stationary phase formula. So they understand perturbatively this integral, and they are able to derive the Kontsevich star product quantizing our Poisson manifold just using these field ideas. And another source of example is just looking into knot invariants that was done, I believe, what Witten, these ideas, just looking in something called Chern-Simons, so you have a quadratic Lie algebra and make sense of this kind of path integral, but here is not perturbatively, and then you come with topological invariants of knots. So an extension of this Chern-Simons theory, instead of looking into a quadratic Lie algebra, you can think that a quadratic Lie algebra is just a current algebroid over a point, and then you can define something called the current sigma model. Then the question is, which kind of invariants can I compute looking into this current sigma model? So what motivate our talk here is just starting with a Poisson manifold. And then, in this Poisson manifold, we can just build the Poisson sigma model. And there is another thing that we can do, is just look into the graph of the Poisson bivector inside of the standard current algebroid. And then this gives us a Dirac structure. So is there any relation between the Poisson sigma model of our manifold and the current sigma model of the standard with incorporating this Dirac structure? And well, what we find is that the way that we need to do is just look into this Dirac structure as a boundary condition, and then we find that the current sigma model of the standard Dirac, of the standard Courant algebroid with the Dirac structure induced by the Poisson manifold is related with the Poisson sigma model, but not of our manifold, just of the local symplectic groupoid integrating our manifold. So I will, yeah. Yeah, that's it. So it's a dimensional reduction. I will explain that. So this is just where we want to arrive, and I will make sense of all these symbols here during the talk. So let me put here the result, and I want to just to make sense of what means this Courant sigma model, what means the Poisson, and what means this equality over here. So the Courant sigma model of the standard Courant algebroid with this boundary condition have some dimensional reduction to the Poisson sigma model of the symplectic groupoid or local symplectic groupoid integrating our Poisson structure. So I want to make sense of this thing. So let me just start with the Poisson sigma model. So what is the Poisson sigma model? We need just a closed surface and a Poisson manifold, and then we can construct the space of fields are just vector bundle maps from the tangent to the cotangent of our manifold. So we have two fields. And then the action of the Poisson sigma model is just given by this integral. So for example, the first term is something that have values in the, where is this? In the cotangent bundle, and these have values in the tangent. So you just pair, and you get a two form in sigma, and you integrate it. So there's a number. And the second part is the same. So what happens here is that this action has some gauge symmetries coming from the Lie algebroid structure of the cotangent bundle of our Poisson manifold. And you can think that these are just cotangent paths, and these give you cotangent homotopies. And the presence of these gauge symmetries make that this path integral over here is not even well defined by the stationary phase formula, because now the critical points came in families. So let me write over here the Poisson sigma model, that we don't forget it. So what I need, Poisson sigma model, what I need is just a closed surface, and a Poisson manifold, and I just write over here the two fields, and this is just a one form on sigma with values on the cotangent bundle, and just I want to write also the gauge symmetries. And the other one is nieta I goes to nieta I plus epsilon d of beta I plus pi jk neta j beta k. Okay, so this is the Poisson sigma model, and as Anton was saying, is two-dimensional. And now what we have is the Courant sigma model that is a three-dimensional sigma model. So what we need is a closed three-dimensional manifold and a Courant algebroid. And then the space of fields, we have three fields, just a smooth map between our three manifold and the base of the Courant algebroid, a one form with values in the Courant algebroid, and a two form with values in the cotangent bundle of the base of the Courant algebroid, and the action is given by this strange formula over there. So what I want to write right now is just the Courant sigma model for the standard Courant algebroid, the standard Courant sigma model. So I believe that all of you know, like, this formula for the standard bracket of the current bracket here, and this is just projection to Tm part, and the formula that we have A bar B bar is just the Lie bracket of vector fields plus the Lie derivative here acting and the contraction over there. So what happens is that now if I'm looking into A and B being, so A here and A bar are vector fields on M, and the B bar are one forms. If I'm look just into coordinate vector fields, then what happens is that this expression is always 0, and the pairing is just a delta. Then the T over there is cancelled, and the G gives just a delta, and the bracket is also like a delta. Therefore, what I have is that the space of fields over here are just X that goes from the closed 3 manifold into M. I call it a field A that is a one form on sigma 3 with values in the tangent bundle, and a B part that is also a one form of sigma 3 with values in the cotangent bundle. And the sum of these two parts is just what I'm calling here E. And I have the P that is a two form on sigma 3s with values in the cotangent bundle. Therefore, the action here is just given by this expression. So it's integration over sigma 3 of Pi dxi plus ai dbi minus ai pi. So this is like the framework that we are working with. So in one side, I have the Poisson sigma model, and in the other, I have the current sigma model. One is 3-dimensional, the other thing is 2-dimensional. And what I want to explain right now is, as happened in the Poisson sigma model, the gate symmetries was coming from the Lie algebroid structure. What happens here is that the gate symmetries come from the Lie 2 algebroid structure of the current algebroid that was described by Bursztyn and Reutenberg. So what I want to explain right now is how to make sense of this kind of integrals by some physical tricks. The first one is just that, well, normally we have these gate symmetries, then our integrals are not well defined. So what we have is just replace what we have over here with an extended theory that right now the fields are just supermanifolds, symplectic supermanifolds, and we change the integration over all fields just by a Lagrangian submanifold, and we have also an extended action. So the other thing is that once you are in this framework, there is a geometrical way of obtaining just field theories that was discovered by Alexandrov, Kontsevich, Svarta, and Zaboronovsky, and our colleagues just take it as sigma models. And this is a geometric way, so you just have a surface, or you just have an n manifold, and you give an n-1 symplectic Q manifold, and then this mechanism produces you a field theory in this Batalin-Vilkovitsky world. Then what happens is that for n equal 1, what we have is the Poisson sigma model, or an extended version of the Poisson sigma model. And for n equals 2, just this gives the current sigma model. And the important thing of this point of view is that we can include boundary conditions right now, because for me here, what I have are just closed surface. And the third trick that I need is this dimensional reduction. So suppose that now our space of fields is just of product type, and the action is also of product type, so everything is of product type. Then you just integrate along one of the factors, and then you obtain a new effective theory, but now that localizes over some fields on this factor that you are not integrating. So this is like how you need to understand this relation between the Courant sigma model and the Poisson sigma model. So you just understand it as integration, as partial integration over one of the factors that are just like expressing the high energies interactions. So let me say how works this AQST boundaries condition. So what you have in the target are just symplectic Q manifolds, and what you can put as boundary conditions are Lagrangian Q submanifolds. So for n equal to 2, we have that the targets are in one-to-one correspondence with Courant algebroids. And then the Lagrangian Q submanifolds are just the Dirac structures on these Courant algebroids. Therefore, Dirac structures can be good boundary conditions for this Courant sigma model. And this is the way that we are using. And then the only thing that we need to impose is that the image of the fields in the boundary take place on the Dirac structure. So, okay, right now I explain what is the Courant sigma model, what is the boundary conditions, I explain what is the Poisson sigma model, so let me just talk a bit about local symplectic groupoids. So suppose that you have just a Poisson manifold, and then a Poisson sprite is just a vector field compatible with your underlying Poisson structure, satisfying these two conditions. And using this Poisson sprite, then you can find a neighborhood of the zero section on your cotangent bundle such that this neighborhood have a symplectic form in a way that this is the projection map of the cotangent bundle to the base is just a symplectic realization given by this formula. And what happens of this kind of neighborhoods is like this is not just a neighborhood, in fact, have the structure of a local symplectic groupoid. And the other thing is that if you have any symplectic groupoid around the units, you can think that your symplectic groupoid is isomorphic to this local model over here. So in some sense, we are not losing too much information. So right now that I have all the ingredients, I can make a precise statement of our result. So we have just a closed surface on our Poisson manifold, and what we claim is that the Courant sigma model of this closed surface times the open interval with boundary conditions given by this Dirac structure has dimensional reduction to the Poisson sigma model in that surface, but with target given by the local symplectic groupoid integrating your Poisson manifold. So, oh yeah, sure. Well, I'm calling this a result, not a theorem. So I believe that maybe there are some physical tricks over there.
No, but is there a mass theorem which is behind? Are you like proving something?
Yeah,
Okay.
yeah. We believe. I believe that yeah, there is a real.
Could you make precise what you are proving?
For the functionals, the relation between the functionals.
Yeah.
It's non-rigorous if you want to
So
use these on a path.
yeah. So.
The functional part.
So what we are proving is that really this functional over here of the Courant sigma model have an effective theory given by the Poisson sigma model of the symplectic groupoid.
Effective theory, I think, well, it includes, as you say, performing partial integration over everything.
Yeah, that's it.
But probably behind it there is still a calculation which is rigorous. What is it?
Well, I will give a, let's say, let's give this, let's give this idea of the proof of how we did it. And so before to give this idea of the proof, let me say, so there are two things. One here is that we are just obtaining the local symplectic groupoid. And maybe what you want to relate is the Courant sigma model with the Poisson sigma model of your Poisson manifold. Then Alejandro have also a relation between these two things that can be understood now not as a dimensional reduction, but a fiber integration. And the other thing of understanding this result is as a tubular neighborhood, as a Collar neighborhood result around the boundary. And maybe this will be interested if you are interested in the cutting and gluing of your topological quantum field theory. So let me give an idea of the proof. So the first thing that you must do is just replace boundary conditions by bulk conditions. And this is done by this beta field transformation. So you understand the Poisson structure as a beta field transformation between the standard Courant algebroid and just the Courant algebroid given by the Levi algebroid structure induced by the Poisson manifold. And what happens is that this sends your boundary condition to just the boundary condition given by the zero, so the cotangent boundary condition. Over that, what we do is just divide the fields into two parts, the fields that contain the dt part and the fields that doesn't contain. And this decomposition give really a decomposition between two sectors of your big theory, of your Batalin-Vilkovitsky big theory. And therefore, we can do a partial integration over here, over this factor, using this gauge fixing, just the axial gauge fixing. And once you do that, what you obtain is that the theory localizes over these kind of fields. And if you look to these kind of equations are just really the symmetries given by the Poisson sigma model. So this is like a cotangent path in the t direction, and this is a tangent vector to the cotangent path in this t direction. So the reduced action that we obtain is just this one over here in the localized theory. And what happens is that this reduced action also have some invariants over gauge symmetries that are, if the first row over here are just, once more, tangent, cotangent path and cotangent homotopies, and this is tangent to cotangent path, and this is tangent to cotangent homotopies. Therefore, if you choose a Poisson spray, you just can make the independence of this t direction using this Poisson spray, and this gives you just a gauge fixing over the orbits of these gauge symmetries. And what we obtain is just that this reduced action over the localization of the vector fields is just given by this action here. That is exactly the Poisson sigma model action of your local symplectic groupoid integration in your Poisson manifold. I don't know if this answered your question, Anton, or?
No, I'm not sure. Like this step 5, right?
Uh-huh.
What you said the reduced action is given by, but like kind of what's the relation between the two functionals? Maybe I haven't quite understood.
Okay, so the relation really is that you produce that fiber integration and you have this relation over, where is it? Over here. So this is the relation that you have between the big one computation and the computation over the reduced fields, where this delta here are precisely this cotangent path in the t direction. Okay, so basically this is what we believe that we prove, and I believe that this is really a proof. And well, just the last things is just further directions in this project. So what happens with general Dirac structures? Is there any kind of dimensional reduction? And the second thing is if you can use the Courant sigma model to compute two morphisms into the pictures. And there are some like guess of what's happened. So the first one is that if you look to n equal to, then you have two morphisms into the picture. And then the Cattaneo-Felder thing, derivation of the star product, says you that you must use the Poisson sigma model to compute the star products. And then there is a result of Bursztyn, Dolgushev, and Waldman that say that the Morita equivalence between the star products is given by the orbits of this group over here. And now you can recognize that this group are preserved with the group of diffeomorphisms of the standard Courant algebroid. So you must, I believe that if you put two boundary conditions, then you can use the Courant sigma model to compute Morita equivalence also at the quantum level between these Dirac structures. So that's all. Thank you.